Hey gang, and welcome back to another video here on JoChem. Okay gang, if you're coming from the Hemiacetal video, then you're in the right place, because this is kind of like the, hand-in-hand partner video for that Hemiacetal video, because in this one, we are talking about Haworth projections, and I couldn't get around not mentioning them in the previous video, because when you do Hemiacetal formation with, sugars, and you go from a Fischer projection, the very natural next thing you see, that representation of the cyclic structure, is a Haworth projection. So here's where we will officially talk about them. So what are Haworth projections? So Haworth projections are, and what I'm going to do is just draw a kind of blank six-membered ring one down here, is just kind of like a ring view, and it's very similar to what you would see if this was a chair. So it's kind of like if you had this chair, but we're looking at it like this, completely just at a flattened view of a ring like this. So what I'm trying to show is that these are closer to you, these kind of three carbons right here, like this one, or these two rather, these ones are coming out at us, but it is very flat. So it is kind of like you're looking at this thing just kind of straight on like that. So when you have a six-membered ring like this with oxygen embedded in it for carbohydrates, you will kind of see these referred to as a Pyranose, okay? So that's when you have six elements of your ring, and again for carbohydrate. And you will also see this, and we will do some examples, we'll look at examples, when you have it in a five-membered ring. So this, instead of being a Pyranose, the prefix you'll see is that this is a furanose, okay? So this really means five, this really means six, okay? In terms of these rings with the oxygens embedded in them. Here we have the ability to also draw this as a chair, but you will only see the five-membered rings kind of in this Haworth projection. Otherwise, you'll just draw them like a regular five-membered ring. Okay, anyways, we're not gonna talk about these for a little bit. I just wanna focus in on this. Okay, so the Haworth projection is just when you're looking at it kind of on a side, and every position on a Haworth projection, right, you either have up or down. So at every single position, up or down like this. So if this, for example, was on a cyclohexane ring, the nice thing is that really the Haworth projection isn't anything quote unquote new. There's still just the concept of up and down on a ring. So again, if on, and I didn't even number this the same way, right? What I wanted to do was say this was 1, this was 2, this was 3, 4, 5, and 6. So if just for example, if I said something was up here, like an OH was up and an H was down, then that, I could directly draw this ring where I say, okay, the OH is up. Well, up here is equatorial and down here is axial. So again, it's just like flattening stuff out. You're not really thinking in terms of axial and equatorial. You just want to see, on a given ring like this that's flattened, what's up and what is down. And if you need to analyze further for whatever reason, it's really easy to draw the chair form of a Haworth projection, because once you've gone from here to here, you've already done the hard work of figuring out what's up and what's down. From here to here, you just need to figure out, okay, is up equatorial or axial at a given position. Okay, so there is some extra terminology that I do want to drill into and some extra concepts we need to cover. So I want to do that now. So I'll erase this. Now, just to rehash the Hemiacetal formation very quickly. Remember, this happens in acid, and this all happens because we protonate our carbonyl oxygen. We know that means we'll have a plus charge here. We have this down here, 1, 2, 3, 4. Right, left, right. Fill in my hydrogens. And then remember, the whole idea is that it's the oxygen at the bottom that really determines the D or L-ness of your carbohydrate that does the attack. Because for forming a Pyranose, right, six-membered ring like this, we're going to have 1, 2, 3, 4, 5, and 6. Now, remember, for ease and also showing what was on top and on bottom of the ring we're about to form, what I like to do is do a double switch about this bottom carbon. Okay, I'll show you. You might not always have to do this, but I'm going to show you it again. So I'm going to switch the OH into CHO2 OH. That's one switch. And then remember, that only inverts the stereochemistry. We need one more. So I'm going to flip. I'll put an H. I'll put the H over here, and then I'll put the CH2 OH over here. Now remember, and I did briefly go over this in the last video, it's at this point that we do our attack. And we boot our electrons onto oxygen, because remember, the protonation activates this carbonyl carbon, makes it more partially positive, gives this oxygen that's neutral but still nucleophilic due to being partially negative a greater incentive to attack. Now, I guess I should do like equilibrium arrows. Remember, when this is the step where we form our Haworth projection, our cyclic structure. Now, we have carbons 1 through 6 here. Now, I'll renumber that as 6. And I said this in the last video, but what I like to do is, if you're looking at this from your, your paper, looking down at it, mentally go to the side, like tilt your head to the side of your desk. You almost want to just like blow it on over, topple it. Okay? What that does, and again, the other way you can do this is, this will be your template, right? If you're forming a 6-membered ring, you're going to have this going on. And there we go. Well, not very good. There we go. Okay, so you're going to have this, right? Now, I like this approach because when you do this like this sideways, it's whatever's on the right goes below the ring, and whatever's on the left goes above the ring. So on position 2, because we know this position right here, which I'm going to call the anomeric position, and I want to dive deeper into why that is called that, right? This is position 6. This is 1, 2, 3, 4, and 5. So on position 2, you can see with the OH being on the right, it's down. So on position 2, we get a down OH, and the H would be up, but on a Haworth projection, if you drew all the hydrogens, it's going to look very busy. I encourage you not to do that. You won't see anyone really doing that. Then on 3, for example, okay, we tilt the thing over. All right, the OH is up, so then you just draw it up, okay? And then for 4, you'll see, okay, it's down. And then last but not least, 5, the CH2OH is up. And you don't be, thrown off if you see someone draw stuff like this. This is still a CH2OH, okay? Now, in the last video I mentioned, because this is an attack on an sp2 carbon, right, that is trigonal planar, there is no preference for the OH that's attacking intramolecularly to attack from on top or on bottom, okay? This is called the anomeric position because you get 2 results. When you attack from the top, right, then this gets the resulting OH gets thrown down. But if you attack from the bottom, the OH gets thrown up. So that's why you will very commonly see the squiggle, which signifies you'll get both, okay? Now, we're going to talk about how you name these structures because, we talked about this being an aldohexose, right? Which really tells you, if you say D-glucose, someone that knows sugar chemistry will know you're referring to this in the Fischer projection form. There's different terminology that involves the Pyranose that will tell you, hey, I'm actually talking about D-glucose, but in its cyclic form. However, there's also terminology to tell someone, hey, by the way, I'm actually talking about the OH, that was attacked at the anomeric, the OH at the anomeric position, whether it's down or up, because this has no bearing on the identity of D-glucose. It's everything else, right? It's this down OH, it's this up OH, it's this down OH that you also see in this structure. That is what defines D-glucose, whether it's in a straight line form or its cyclic form. So this change, this being down or this being up definitely gives the sugar different properties. However, you still have D-glucose. It's just a slightly different version. So in this situation right here, right, if we look at the anomeric position right here, when your anomeric OH, right, is the opposite, on the opposite side of where your CH2OH is, right, you see this is up and this is down, right, so it's the relationship between these two things. You can say the anomeric position is alpha, okay? that's when they are trans to one another, right? They are on opposite sides of the ring. On the other, on the other side, like situation, these are on the same side of the ring. So then you can say this is beta, okay? So if you wanted to put that all together, right, the name, this is alpha D, and it's not glucose, right? It's gluco. You cut off the end, and then you slap on a glucopyranose, okay? And then over here, then you would say, okay, this is beta D glucopyranose, okay? So there, you can see that if you just say D-glucose, someone might, they will default to the Fischer projection form, but if you wanted to be very specific about the cyclic version of D-glucose, then if it matters, make sure you specify alpha or beta, because that tells you what kind of, if you didn't specify alpha or beta, then someone would probably just think this right here. They think, oh, they're not really specifying anything specific at the anomeric position, so I'll just leave it as is. But if you say alpha D glucopyranose, they'll think, okay, I need a ring. That's what the pyranose means. It's D-glucose, so that defines the rest of this stuff. This D defines this. I'll talk about that in a second. And alpha means the anomeric position is on the other side of where the CH2OH is. But if someone said beta D-glucopyranose, then you'd say, oh, the anomeric position is cis, or on the same side of the ring as the CH2OH. Okay, gang, I know that was a lot. What I want to do is take two different structures and say, let's draw the Haworth projection for blank, like D talos or something like that. I want to do it with a aldohexose, and I want to do it with a ketohexose, because what you'll see is one pyranose example from scratch and one furanose example from scratch. So stick with me, I'm going to erase this and we will finish this video out. Okay, gang, doing these two quick examples, I want to show you how if someone, and just ignore this because I drew this beforehand for convenience, if someone were to hit you with a problem like draw alpha L altropyranose or draw beta D fructofuranose, how do you go about doing that? So the very first thing, in my opinion, is you want to extract the information in terms of what sugar are you starting from, what Fischer, get to a Fischer projection. In this problem, which we'll tackle first, if you look at this, this tells you we're looking for L-altrose, right? So you'd go to your Fischer projection sugar table, a list of your D sugars. You then find D-altrose, and then you get the enantiomer, and that right here is L-altrose, okay? So from there, you want to act, and again, you don't have to do this all in your head, but you'll get very good at drawing these. So for example, and one thing I didn't mention before that I want to mention now, not only is this your template, but I want you to almost think of, for a pyranose, and this will qualify for furanose as well. If you think of this can be your template for, because when you really draw CH2OH on a ring like this, you're really cementing where this OH is. Because remember, I've always been doing that double switch, but it's to ultimately find out where the CH2OH fits on the Haworth projection. So the thing is this is for D sugars. Your CH2OH will always be up. And that's a given. Take that to the bank. So knowing that this is L, you can think to yourself, okay, well, the CH2OH is just below the ring. So this is kind of like your template for L sugars, if you will, if you are drawing a pyranose, okay? So from there, right, and again, I'll prove it to you. So if we did a switch here, and then, right, I'd have the OH at the bottom, I'd have the CH2OH up here temporarily, because then I'll flip the H and the H here, and then the CH2OH here, because what we're going to do next is we're going to tip this over, right? We're going to blow this over, and I think what you'll see is the CH2OH ends up on the bottom. So what you can see here is this carbon is this carbon. I'm going to not talk about the I'll do the anomeric position last. This OH is down, and then the other two are both up, up, up. And by the way, there's no right or wrong in terms of like how you structure and like draw the up and the down. As long as it's up and as long as it's down, that's fine. Spatially, arrange things so that it looks pretty. Now, remember, alpha. This means that the CH2OH and the anomeric alcohol are trans. Now, I wanted to do an example of L because now the CH2OH is down, which means to make sure that I'm honoring the trans, definition of what it means to be alpha, that means that the anomeric alcohol needs to be up. So don't cement that in your brain that beta is up, alpha is down. Think of it as beta is being cis to the CH2OH and alpha is being trans to it because, the CH2OH will flip whether you have a D sugar or an L sugar. Okay, now down here, again, what do we have? We have D fructose, okay? So that's why you see I have the D fructose Fischer projection. Now, why I wanted to do this problem is we have a furanose. So what does that template look like, right? So you're going to have furanose means 5. So now we have a 5-membered ring. So you will have a cyclopentane vibe, right? But it's not cyclopentane because we don't have 5 carbons in there. We have an oxygen. So what does that look like? Well, this is your anomeric carbon, and 2, 3, 4. But very similarly, you have your OH right there. So again, just to prove to you that at this position you will have a CH2OH, because if this is 5, then anomeric is 1, 2, 3, and then 4. So on carbon 4, you have your 1 CH2OH, and you'll see why I said 1 CH2OH. But you'll have this, and I'll prove this to you, because again, we'd want to put this on the bottom for the sake of being like, how we tip our Fischer projection over. So at first we'd have OH over here, CH2OH, and then that was 1 switch, we need to do 2. H over here, CH2OH over here. So if we tip it over, the CH2OH is in fact up. Now, I'll actually start with the anomeric carbon. We see this is beta. So the anomeric alcohol and the CH2OH will be on the same side. So we actually have this as going up, okay? And then you just do the rest. So on carbon 2, the OH is, I'm going to erase the number so I can actually fit this in. It's going to be up. And then on 3, it will be down. So this, my friends, is beta D fructofuranase. And one quick thing I realized I missed on the first take of the examples part of this video, gang, was yes, this is beta D fructofuranase, right? This is D fructose. But one thing I missed in that, and you probably caught it, and you were probably jumping to the keyboard to leave a comment, was, so at the anomeric position, which is carbon, and I numbered incorrectly yet again, this would be 1, 2, 3, 4, and 5. So on position 1, when we do have this attack occur, right, with the protonated carbonyl oxygen in the ketone, right, the beta defines that on the anomeric position, we must have the OH going, being on the same side of the ring, being cis to our CH2OH on the bottom part of the ring. As a result, right, and you only have to worry about this with ketoses, because we are not at the end of our ring, this first position has a group off of it. It's a CH2OH itself, right? So because this OH, when this planar carbon, this is planar, must be, when it gets attacked, the resulting OH that's attached to carbon 1 goes up, and the resulting CH2OH that carbon 1 also has attached to it must go down. So if this was alpha, for example, the only thing that would change would be this OH goes down, this CH2, this would be the alpha version of this, right? And then the rest would stay the same. But I just wanted to let you know that I had initially forgotten to draw it. I have it right on my, my notes and everything like that. But don't forget when you're working with ketoses, right? you're going to have an extra CH2OH. And just not to forget about it. Okay, on to mutarotation. Okay, gang, to close out this video, I want to talk about the concept of mutarotation. So you're going to see this equilibrium, and this is the same equilibrium I showed at the very beginning of the video and the very beginning of the hemiacetal video. But I like this representation a little bit better because it really shows that when you have your Fischer projection, right, I know I've been a broken record, the cyclic form of the sugar is preferred, right? And you need acidic conditions to get there. However, it's not like from here, it is from here that you either end up with the beta, what you can call anomer. When you say the word anomer, you refer to the whole structure. So I could call this, the beta anomer of D-glucose. I could call this the alpha anomer of D-glucose. So what's important to know is, you go from D-glucose to, say, for example, the beta version, the beta anomer of D-glucose. You end up being beta D-glucopyranose. And yes, that's heavily favored, but eventually a little bit of this will flip back to the Fischer projection form. And then maybe from there, it becomes alpha D-glucopyranose. So it's kind of like the Fischer projection is the swivel point between how you get the beta version and the alpha version. You can't go straight between these two. You have to unravel, become straight chain again, and then become the other version of the anomer. And it's that phenomenon that is mutarotation. It's the fact that this position can be changing all the time. It's not like you go from straight chain Fischer projection to the cyclic form and you stay there, you never change. No, you can definitely go back and forth. And not only when you go back here, you might end up, being the other type of beta anomer. And I think, acidic conditions will do that. And essentially what happens, right, is you reform your carbonyl-carbon double bond, and then you kick this off, and there's going to be some acid-base things that will happen to make sure you actually get back to this form and you don't have charges, but you get the idea that just like we learned it when we did acetal and hemiacetal formation for the first time, this is a reversible reaction. So it's constantly going back and forth. Obviously, we've talked about how this form is favored, but once you go back to the Fischer projection, you may not go back to where you just came from. You might become a different anomer. Okay, gang, that is the concept of mutarotation and Haworth projection drawing. I hope if you had any confusion about that stuff, it's cleared up. If you're watching me from YouTube, if you're here on JoChem, watching from YouTube, thank you so much. Make sure to check out this video on jochem.io, link in the description, because there's a guided worksheet with solutions, just practicing what we just talked about, and it's all for free. And if you're watching me from JoChem, then you rock. No matter what, I hope to see you all in the next video.